Welcome, everyone. My name is Anton, and today I'd like to present a new addition to the data source V2 API that allows connectors to control the distribution and ordering of the incoming data. While the topic may sound specific to folks who build and provide their own connectors, it is actually very important for data engineers that leverage those connectors as well. Distributing data and ordering data correctly will save you a lot of resources and time. A few words about me. I'm an Apache Iceberg PMC member and Apache Spark contributor at Apple. My current focus is on making data lakes reliable and efficient at scale, which requires not only refining query engine, but also a table and file formats. Apart from that, I'm a big fan of open source. I truly believe that's the only way to build industry standards. So if you happen to have a topic or a question that is related to the work that I do, feel free to reach out to me as well. I would be glad to discuss that with you. Today, I'll start with the motivation behind the new data source V2 API. Then I'll move on to the main part of the presentation, where we will talk about why data distribution and ordering are so important and how connectors can control them. And at the end, I'll finish by outlining some remaining work. All right, so what's actually run with the V1 API? Why do you need another data source API? And first of all, there are reliability problems, and specifically the behavior of the data frame writer is not properly defined. And Spark delegates a lot of decisions that should be made by Spark to connectors. And unfortunately, different connectors tend to behave differently under the same circumstances. For example, what is the override save mode supposed to mean if there is an existing table? Some connectors perform partition overrides, maybe dynamic, maybe static. Some truncate the table and add new data. Some actually drop the table and create a new one with potentially another schema and another partition in spec. Learning those differences and memorizing is really frustrating for the user. To make things worse, Spark internally has a number of logical plans for more or less the same commands, which makes maintaining the right path pretty hard. The last point also contributes to another problem. The delegation rules are not always consistent because you have so many logical plans, so different rules capture different plans. Also, there is no schema checks at all for writing to path-based tables. This means you can write whatever you want and Spark will never complain. Unless you try to read the data back, of course. In this case, Spark will try to make sense of the data that's available in that location and will fail if it doesn't make any sense. Apart from reliability concerns, connectors have to interact with a few internal APIs like SQL context or RDPs. This makes evolution of Spark internals a bit harder for the community. It is also pretty tough to add new features to the V1 API. If, for example, you want to add limit or aggregate pushdown support, which is something that's being discussed for years in the community, you will have to do probably a lot of overloading prune filter scan. The same applies to exposing the column of Edge API because the existing code depends a lot on RDB and rows. Finally, some of the features are simply not available, right? You have neither structure streaming nor multi-catalog support. And support for bucketed tables is extremely limited because you can use only the built-in hash function in Spark, and you cannot leverage, you cannot benefit from join optimizations if you have any other type of bucketing. So if you have Hive bucketing or Iceberg bucketing, you cannot really skip shuffle stages. To summarize, the V1 API is pretty popular, it's stable, and works pretty well in simple engineering use cases. But if you want some advanced functionality, that's where you want to consider migrating to the V2 API. Due to all of those issues that I just described, the community has decided to offer a new V2 API, which we will cover next. And first of all, Spark ensures that all V2 connectors will have predictable and reliable behavior. For example, instead of passing a save mode and letting connectors interpret it, Spark will now use the new catalog API to check if a given table exists. And if yes, then it will run the same validation rules independently of the underlying connector implementation. So that way, you always have consistent behavior and validation for all V2 connectors. Also, a lot of community effort went into designing and standardizing logical and physical plans. So hopefully it should be a lot easier to evolve and support the new write paths. Plus, if you're doing explain commands to see what actually got executed, you should probably see more detailed write down, more accurate logical and physical plans, which would make more sense for you. There are also proper instructions in place. So you no longer interact with any internal APIs like SQL, context, or RDD. You just interact with internal row and columnar batch, and if you connector-specific interfaces. Also, instead of relying on overloading, there are mixed-in traits that you can implement to indicate Spark that you support specific optional functionality. The new API also supports multiple catalogs per session, essentially enabling catalog federation. So you finally can talk to multiple meta stores in a single job. That's something that is a highly anticipated feature. You also have a full structured streaming support, so you can provide custom sync and source. The new APIs also allow you to leverage the vectorization. So you can speed up your query by exposing columnar batches instead of rows. There's also a very interesting effort that I would really love to see done is around partition joins, which should enable join optimizations for Hive bucketed tables or for Iceberg bucketed tables, or for actually any type of bucketing that you might have. Okay, so hopefully I have convinced you to consider migrating to the new API by now. Let's move on and talk about data distribution and ordering, and I'll start by clarifying what those terms actually mean. As we all know, Spark has multiple tasks in a single job, and distribution will define how the data is split between those tasks. Let's consider an example where two tasks basically contain records for 3 years, for 2019, 2020, and 2021. If I ask Spark to cluster this data, which is one way to distribute it, Spark will shuffle this data around so that all records for a given year will be in the same task. In the provided example, both original tasks contain records for 2019, but after we did clustering, all the records ended up in task 1. It is really important to emphasize that distribution bears no guarantees about the order of the data within tasks. So in our example, records for year 21, 20, essentially for 2021 are not next to each other. They are in random order. And distribution basically ensures that they are in the same task, but it has no guarantees that they will be next to each other within that task. Ordering, on the other hand, controls the order of the data within tasks. If I ask Spark to order the data we had in the previous example, it will sort the records, but it will not sort them across the tasks. Essentially, ordering does not change the set of records in a task, but it can reorder them. In the provided examples, both original tasks contain records for 2019, and that still applies after the ordering. It's pretty much the same, except that the records are now ordered by year. Okay, so you see that distribution and ordering are pretty independent. That's why you would probably need both if you trying to optimize your write or read performance. A valid question would be like, why would anybody actually care about these two? And as it turns out, these two aspects have a profound impact on the overall table performance. If you're working with the built-in file source, or if you're working with Iceberg, then data distribution and ordering will impact the number of generated files. If you use columnar file formats like Parquet or C, then we're even in a worse situation, as Parquet, for example, has to buffer the incoming records before they're written to disk as a single row group. And buffering requires more effort. So if you don't order your data correctly and don't distribute it correctly, then your clusters will consume more memory. That's why I believe that tuning data distribution and ordering is really essential for the right performance. In many cases, doing a bit of extra work before starting the actual write can be very beneficial. Let me give you a couple of examples. Let's say we have a job with 1,000 tasks, and each task contains records for day 1 to day 1,000. And our destination table is partitioned by day, right? And without proper distribution, each Spark task may have data for every single partition. This is essentially what you see on the slide right now. This means that each task will have to write to 1,000 partitions, producing 1,000 files with 1 record each. Totally, this will be 1 million files per batch. And this will put a lot of pressure on the underlying storage. And if you're working with Iceberg, this will be a lot of pressure on the Iceberg table, because if you run this for months, right, or for a year, this will be a lot of files. That's why you would need to aggressively compact these tables and expire all files. And this will end up consuming way more resources and time than by doing something on write. Moreover, you cannot really immediately discard the old files, as some older readers may depend on them. So you will still need to keep them around for some time, essentially doubling the storage cost. At the same time, if you distributed your records correctly, you would have prevented this issue altogether. And the example here, we distributed the data perfectly so that each task has just records for a single day, meaning that each task will write 1 new file, and this will be overall 1,000 files per batch, which is a substantially less, fewer files than basically 1 million files. Similarly, the order of the data is quite important. Let's consider Iceberg and the file source as examples. In Iceberg, whenever the task is writing data, it will keep only a single open file at a time. And whenever Iceberg sees records for the next partition, it will close the current file and open a new one. In the example that you see, the data within the task is in random order. So you have the record for day 1, followed by the record for day 2, and then record for day 1 again. Under this default behavior, in the worst case, Iceberg will produce 4 new files, where each file will contain just a single record. Iceberg is smart enough to prevent this, and if you try to do this, it will actually throw you an exception, but I just wanted to convey the point and show this extreme use case. You can also enable the fan-out writer, which will keep all files open until the task is done. But do that at your own risk, because this will potentially consume a lot of memory, because for every single file, the memory consumption will be substantial if you're working with Parquet or C. Like in the worst case, it's proportional to your row group size. That's why if you spend a bit of time and order the data within that task, then you would have prevented this issue from happening. Ordering the data within a task is extremely cheap, right? So you don't shuffle the data. That's why I always advise people to do at least this optimization so that you can keep only a single file open and also write the minimum number of files. Apart from writes, data distribution and ordering will also impact your reads. For example, the built-in file sort supports skipping of row groups in Parquet using min-max statistics. By doing a bit of extra work on write, you make sure that min-max statistics is actually usable, right? And you can skip those row groups. In Iceberg, it's even more critical because Iceberg supports file filtering using min-max indexing. Therefore, by doing that global sort and write, you make sure you can skip files and just limit the scope of your operations to a small subset of files. That's why I highly advise all Iceberg users to make sure they configure a proper sort key in their table, and Iceberg will persist that sort key. And this will highly impact not only your reads, but also operations like migrating. We've seen examples where petabyte scale tables were queried in 5 or 6 seconds overall time because distribution and indexing actually allowed us to do that. Also, data distribution and ordering will impact the storage footprint you have. In particular, columnar encodings perform way better on sorted data. So if you sort your data globally, then you increase the chances of using dictionary or maybe delta encoding, which will reduce the storage size, the size and disk essentially. Also, dictionary encoding is extremely beneficial for your queries, because if you're looking for a given set of keys, you will be able to check the dictionary and you will immediately know if you need to read that row group or not. And this will allow you to skip irrelevant row groups. Okay, so we've covered why data distribution and ordering are so important. Now the question, how do connectors control this, right? And since we want connectors get a data frame with records they need to write, they can apply arbitrary transformations. And built-in connectors, for example, sort data within tasks using partition and bucketing columns to avoid the issue that I've just described. Video connectors, unfortunately, have no way to control it as it stands today, which leads to severe performance issues unless it's explicitly handled by the user, which is rare, right? But that's kind of expected. So connectors themselves have to be smart enough to figure that out for the user. And I know a lot of developers who are blocked in their migration to the V2 API because of the lack of this functionality. But I'm also happy to announce that it's fixed in master and should be available in the upcoming Spark 3.2. Internally at Apple, we've been running this in production for quite some time. We're extremely happy with this. Let me spend a couple of minutes and talk to you about the solution we came up with. And while designing the solution, we considered a few use cases that are really important to address. Specifically, if your use case permits, then connectors should be able to request a global sort and write to properly cluster the data within the incoming batch. While doing global sort and write speeds up subsequent reads and also ensures better compression, it also takes more time and needs more resources, as Spark will need to perform a range-based shuffle. Range-based shuffles are expensive as they require a skew estimation step, which is a separate Spark job that allows Spark to determine distribution ranges and also avoid struggler tasks. Range-based shuffles and skew estimations in particular are extremely important, but they come with, they also introduce a bit of performance penalty. If the cost for the skew estimation is too high, then connectors can cluster the data by some expressions instead and then sort the data within those tasks. This option will trigger a hash-based shuffle, which is considerably cheaper than the range-based one. but it also is not as scalable as it can introduce hotspots if your data is not distributed evenly. So be really careful, and if you can survive the global sort, I would definitely recommend doing that. And finally, if your use case requires writing data as quick as possible, then you can do a local sort. Usually that performance overhead is negligible, but if you definitely need to write data as is, you should be able to do that as well. In order to support this functionality, we had to modify the write builder interface. So previously, it used to report methods that constructed batch and streaming writes. Right now, it will build a logical write, and that logical write will be later converted into a batch write or streaming write by Spark Optimizer. And if you need specific distribution or ordering of your data, then you can implement requires distribution and ordering interface, where you can instruct Spark which distribution you want for your data set and what are the expressions you want to order the data by. With respect to supported distribution, we basically support the same distribution Spark has internally. You can request for an order distribution that's the most expensive option that will do the skew estimation to compute the ranges. You have cluster distribution, which will trigger the hash-based shuffle without skew estimation. So again, be careful with it. Do not introduce any hotspots. And you also have unspecified distribution, which is the one where you say, I don't really care how to distribute it. And in order to indicate how you want data to be ordered, you will return an array of sort order expressions. You don't have to implement these expressions yourself. There are utilities that allow you to construct objects of this interface, where you basically say, hey, I would like my data to be ordered by this expression. I would like it to have this direction and this null ordering. Let's talk a bit about the current state. As it stands today, its functionality is fully implemented and functionally mastered for batch queries. Structured streaming support is still in progress. Here's the Jira and results in OpenPR. Structured streaming is a bit harder because it's not hasn't moved properly to the V2 API internally, so we don't have all the logical plans we need at this point. So it is a bit harder, but I'm still hoping we can have this done by Spark 3.2. There are also a few interesting remating features we would like to have, and if you're interested to collaborate, feel free to reach out to me. Internally at Apple, we allow our customers to indicate what distribution and ordering they want to have in the create table statement. And Iceberg, for example, will be able to support that by persisting the sort key in the metadata. We found this extremely useful, and it is supported by a lot of modern data warehouses. So it would be really nice to support this feature in Iceberg, in Spark. Also, there is an ongoing effort to control the number of shuffle partitions. In some of the use cases, it's not enough to say how you want data to be distributed. You actually want to control the number of shuffle partitions it has. So there is an ongoing effort to support that as well. Apart from that, there is an effort to leverage that query execution to call as the partitions during writes. This will require a bit more effort because the call as code doesn't actually keep the same distribution, but this will be also very helpful so that you can not only distribute the data correctly, but you can also write reasonably sized files. Okay, so I'd like to finish with a few key takeaways I want you to remember. First of all, consider migrating to data source v2 if you need more advanced features or if you want to have more reliability. I think it is mature enough so that you can migrate now. Also, never underestimate the importance of data distribution and ordering. This is critical at scale, and this will have a profound impact on your writes, reads, and storage footprint. Also, never don't forget to review and rate sessions. The feedback is important to us, and thank you very much for your time today.